Now, I've been talking about these indexes as just some kind of tree. Let's start to think about the kinds of properties we want these trees to have. Before we go and plug in just any old data structure, though, we have to look at the issues specific to a database system so that we can pick the right data structure. So the biggest differences between a DBMS, which itself is just a program, and any other program, is that a database is dealing with a gigantic data set, much more than you usually have to worry about when writing most programs. And the access order to that data is harder to predict than it is in most programs. So what this means is that for a DBMS, we're going to have to rethink how it interacts with the hardware. It is just a program like any other program. It's running on the same kinds of hardware. So there's a processor with caches, there's main memory DRAM, and beyond that there's a hard drive. And as programmers, we know that if we can rearrange the computation so that it makes more effective use of the cache, and we avoid this interface as much as possible, going to main memory is slow. If we can avoid that interface, then our program will be faster. For a DBMS, though, avoiding this interface is going to be important. With most programs, you don't really have to worry about that because the entire data set fits in RAM. With a database, there's no way we could fit the entire thing in RAM. So this interface to disk becomes much more important, and we have to find ways to avoid going to disk as much as possible, even though the data set is much bigger than what would ever fit in main memory. Here's a nice illustration of the memory hierarchy and how the different levels in it compare to each other. Basically, the further away you get from the registers, the slower it is at each step. So obviously we want to avoid going to those slower, further away levels as much as possible. The general rule of thumb is the faster it is, the smaller it has to be. So it would be great if we could just fit everything in the L1 cache or even in registers, but obviously for a database that's just not feasible. So we have no choice but to go down to these slower levels of the hierarchy. So our goal is going to be, although we have to go to them, we can try to reduce the number of times we have to go to them. But there's also this interesting barrier here. As soon as we go past main memory DRAM, the storage levels become non-volatile. So everything above that is what's called volatile, meaning that when it loses power, it loses the data. So as soon as you turn your computer off, everything in main memory, registers, and cache is just gone. With a database, where we need ACID, we need durability and consistency. Obviously, that's not an option. So another reason why we have no choice but to use the disk. So avoiding these slower and further away levels of the memory hierarchy, though, is not just about performance. It's also about energy. So here's a little graph of where energy is spent for a certain program. And it's broken down into the computational units themselves, like adders, multipliers, and so forth, and then everything else is various memories. So the registers, the L1, DRAM, and so on. And we can see that the computation is only 2.6% of the energy spent. And by energy, I mean actual joules, physical energy. And most of the energy is spent in DRAM, and lots of it is spent in other areas of memory. And normally you don't really think of energy as being a problem. Like your laptop or your personal computer, you probably spend maybe like $2 or $3 a month on the power bill just powering your laptop. But I guarantee you that this is a concern in data centers, where all they're basically doing is moving data around and storing data. One of the biggest costs of running a data center is actually just their power bill. And the more energy the computers are spending, the more energy you also have to spend cooling them. So if your computations are not efficiently arranged to avoid accessing these higher and slower levels of memory, then you're just spending more money on power, and that is a big concern in data centers. So what do we do in a database management system? Can we use DRAM? Well, no, it's too small and it's volatile. So a power outage means data loss. It's just not an option. So, well, what about the disk? It is big. We can put multiple disks. We have plenty of storage in disk form, and it's non-volatile, so that's great. But isn't it too slow? It is very slow. So when we have to run an SQL query, do we have to go out to disk every time? Well, that'll be our goal, is hopefully no. Or if we do, avoid the number of times we have to go to the disk. So we have no choice. We do have to go to disk. It's slow, so our goal is going to be to limit those delays. And then DRAM is going to look more like the cache in a normal program. So normally you try to fit as much into cache as possible. In a DBMS, we're also going to try to fit as much into DRAM as possible and kind of treat it like a cache for performance optimizing purposes. So whatever data structure we use for these indexes, they will have to be designed with efficient disk access in mind.